So, in the previous lecture we had initiated discussions on forced vibration analysis of one dimensional continuous systems. So, in our previous lecture we started with the case of harmonic forcing, which as we discussed is a separable forcing in space and time. So, just to reiterate, let me recapitulate the what we started. So, we were looking at the forced vibration analysis of a system governed by this equation of motion along with boundary conditions, say for example let us say 0 and some initial conditions. So, this was our problem. To this problem we considered, we observed that the solution can be written out as the homogeneous solution which we expanded in terms of the eigenfunctions of the unforced problem. And so, this was the homogeneous solution, and along with that we have the particular solution. Where this capital X is the amplitude function of the particular solution, and these are the eigen functions. So, this is the solution form that we have for a system like this, and when we substitute this solution in the equation of motion, what we obtain is, so this homogeneous solution actually goes to 0 once we substitute in here. The contribution from the particular solution, which can be written upon simplification, and along with this the amplitude function of the particular solution must also respect the boundary conditions. So, for these boundary conditions correspondingly we have these as the boundary conditions on the amplitude function. Now, this we defined as the boundary value problem. So, this is the boundary value problem which we have to solve in order to calculate the amplitude function of the particular solution. So, this is the unknown here, and of course, we have unknowns C k and S k, which must be determined from the initial conditions after we have solved this amplitude function of the particular solution. So, we solve this boundary value problem, determine capital X, substitute it here and then apply the initial conditions to solve for Ck and Sk, and the solution of Ck and Sk we have seen in one of our previous lectures. So, today we are going to focus on the solution of this boundary value problem. Now, in the previous lecture also we discussed about this solution in terms of eigenfunction expansion method using the eigenfunction expansion. Today we are going to look at the solution of this boundary value problem using what is known as the Green's function method. Now, what is this Green's function? So, now, Green's function is the solution of the boundary value problem. So, we write it like this, we represent the Green's function using G, capital G, such that so this was the differential equation of the boundary value problem, as you can see here. So, so the Green's function is a solution of this differential equation with a very special form of q of x, which is the Dirac delta applied at x equal to x bar. So, this is the Dirac delta distribution. And of course, the Green's function also satisfies the boundary conditions of the problem. So, this boundary value problem defines the Green's function. So, you realize that the Green's function is a solution of the with a special forcing in terms of Dirac delta applied at x equal to x bar. So, which means that Green's function is the solution of a one dimensional continuous what we are discussing at present. So, a one dimensional continuous system when you apply a harmonic concentrated forcing of frequency capital omega applied at the location x equal to x bar. So, the solution of that system is the Green's function. So, therefore, the Green's function is a solution is the amplitude at x because of a harmonic forcing of frequency capital omega applied at x bar. So, that is the significance of this Green's function. Now, when we talk about Green's function, we always use homogeneous boundary conditions. So, the boundary conditions must be homogeneous like this. Now, if it is non-homogeneous, then we have discussed in one of our previous lectures how to homogenize the boundary conditions. So, we are going to discuss the Green's function in the context of only homogeneous boundary conditions. Now, how is this solution of the Green's function going to help us in solving a problem with an arbitrary force distribution capital Q of x? So, let us look at that problem. So, let me write again. So, this is the problem of course, with these boundary conditions. This is what we want to solve. We claim that the solution of this, so the amplitude function corresponding to an arbitrary forcing capital Q of x is given by integrating over the domain of the problem performing this integral. So, we integrate over x bar, we integrate over x bar from 0 to L, x bar goes from 0 to L, and we are left with a function of x which is the solution of this problem. So, this is what we have to show. Now, let me rewrite this differential equation as this is only a way of representing this in a short form. So, I will write this as some L, some operator L acting on x gives q. So, this L is so this is L. So, this is only a short way of abbreviated way of writing this whole thing. Now, if this is the solution, let us see what happens. If this is a solution, I substitute this in here. So, L So, this is a linear differential operator. So, I assume that this can commute with this integral, because this integral is over x bar, L is an operator on x. So, here I can write, I can interchange the integral and the operator, and since this acts on functions of x. So, it will act only on g. Now, L acting on g is what we already know. So, this is nothing but L acting on g. So, therefore, this integral actually reduces to delta of x minus x bar. integrated over x bar, and that is nothing but q of x, which is the right hand side. So, which means that this must be a solution to this problem. So, we need to solve for this Green's function, which is for a very special form of force distribution, and which might possibly be quite simple as well, we hope. And once this is done, then we can, given any force distribution, we should be able to contingent on this integration being performed or is doable, then we can easily solve for the amplitude function for an arbitrary forcing, in which case the solution, we can write our solution of the original problem as the homogeneous solution plus the real part of the this argument. So, we can easily find out the total solution, and from here the unknowns can be found by using the initial conditions. Now, the problem remains that how to solve for this G. So, let us take this example of a string once again. So, we have a concentrated harmonic forcing at x equal to x bar. So, this is the problem we are going to solve essentially. So, finding out the Green's function is essentially solving this problem, and if you write down the equation of motion and you substitute the solution form that we have been considering, so we get the boundary value problem So, we are going to solve. So, let me write down the equations. Let us solve a problem like this. So, this with the boundary conditions, so this is the problem we want to solve. The boundary value problem for this can be written as So, this is our boundary value problem. Now, to solve this, what we do is, we are going to look at two regimes of this string. So, one is let me call this as the left regime, and this as the right regime. So, from 0 to x bar is the left L, and from x bar to L is the right regime R. So, in these two regimes, we can rewrite this differential equation of the boundary value problem as so, this differential equation of the boundary value problem over these two regions of the string can be written like this. So, only at x equal to x bar there is this Dirac delta function acting. In the other regions there is no forcing. Now, we can easily write the general solution of for the Green's function in these two regions. So, these solutions can be written as so, over the two regions we have these two solutions. Now, we also have the boundary conditions. Now, we also have the continuity conditions at this junction x equal to x bar. So, you see the solution of of the boundary value problem, the differential equation of the boundary value problem. So, the general solution is given by this. Now, we have these 4 unknown coefficients A L, B L, A R and B R, which are to be solved in order to determine the Green's function. So, we will need 4 conditions for solving these 4 unknowns. Now, 2 conditions are obtained directly from the boundary conditions. One further condition has been obtained from the continuity of the string at x equal to x bar. The 4th condition must of course come from the force condition. So, we have this the force balance at x equal to x bar. Now, this force condition for the string can be easily found by directly integrating the differential equation of the boundary value problem. So, our differential equation of the boundary value problem is given by this. So, if we integrate this both sides of this equation over the domain of the string, then we can easily obtain the 4th condition, which is nothing but the force balance condition at the junction x equal to x bar. Now, here we can, so this therefore implies now over this interval 0 to L, in almost or at almost all points this integrand is 0 except at x equal to x bar. So, this we can write as so, from 0 to x bar minus epsilon, this integrand is 0. From x bar plus epsilon to L, this integrand is again 0. So, it is only a small region around x equal to x bar, we this integrand is non-zero. So, that is what we are interested in finding now. So, you see this term when integrated over such a narrow region from x bar minus epsilon to x bar plus epsilon, since g is a continuous function, as we have already put the condition of continuity on g, for a continuous function g, the integral over a diminishing domain goes to 0. So, because g is continuous and it does not have any sharp discontinuity, etc. Now, this term can be integrated once, and what we have, so this term is not going to contribute in this integral, this term is going to, because the first integral of this will be the slope of, will represent the slope of the string. It will del g del x, that represents the slope of the string. Now, string does not resist bending moment. So, it can have a slope discontinuity. So, therefore, this actually can be written as then that implies so now we have all the conditions required to. So, here we have one condition and here we have three more conditions. So, these four conditions can be used to now solve for these unknown coefficients A L, B L, A R and B R. So, if you use these four conditions and solve for these unknowns and finally put in the Green's function, then what you obtain is so this when x is between 0 and x bar, so this is our Green's function for the string when a concentrated harmonic force of circular frequency capital omega acts at x equal to x bar. Now, this then once we have this Green's function, then corresponding to any force distribution capital Q of x, we have seen that this can be the amplitude function of the particular solution can be written as now we are going to now solve an example and see how this integration can be performed. So, we consider a string with a uniformly distributed harmonic force. So, let us see this. So, this is a string taut string on which we have a uniformly distributed harmonic force we have looked at this example in the previous lecture also. So, let us now solve this same problem with this Green's function method, using the Green's function method. So, we have the equation of motion with the boundary conditions So, we are right now more interested in solving the particular solution. So, this is this is the formulation of the problem for this uniformly harmonically forced taut string. So, the solution is a homogeneous solution plus we have the particular solution in this form, and we have already derived the Green's function, and we need to solve this amplitude function of the particular solution by performing this integral in our case q of x bar. So, I will rewrite this equation so as to match the differential equation for which we solved the Green's function. So, our capital Q of x bar is nothing but this. So, we have to perform this integral of the Green's function from 0 to L. Now, remember that this Green's function is a response of a system of the string when concentrated harmonic force is applied at x equal to x bar. So, this is the response or the amplitude at x is given by this Green's function. Now, we are looking at this string from 0 to L. We want to find out the amplitude function capital X at any location x, an arbitrary location x. Now, this integration has to be performed over x bar from 0 to L. So, if you are interested at a particular location x, the solution at particular location x, then when we perform this integral, there will be a region of this integral from 0 to x and from x to L. So, x bar which must go from 0 to L can be broken up from 0 to x, x bar going from 0 to x and from x to L. So, we are going to actually perform these two integrals. So, let us see what are these two integrals. Now, from 0 to x, so x bar lying between 0 to x, let us once again look at the Green's function. X bar lying between 0 to x. So, which means x bar is less than x. So, this is the function corresponding to this integral, the integrand of this integral. Whereas, from x to L, when x bar is greater than x, x bar is greater than x. So, this must be the integrand. So, let us now carry this out. So, therefore, so this is the first integral. And that is the second integral. Now, performing these integrals is straightforward. So, this and if you simplify these terms, so if you open this So, this is what you obtain, and upon further simplification, so this is obtained as so this is the amplitude function of the particular solution. Now, you can check this expression with what we obtained in the previous lecture when we solved this problem exactly. So, this was exactly the expression of the amplitude function. So, when we solve problems of forcing with Green's function, what we need to look at it is this integral over the domain, and this has to be performed a little carefully, taking into account the regions of the problem of the string, for example, what we have looked at today. Now, this Green's function can also be determined using the modal expansion technique that we discussed in the last lecture. So, let us briefly look at this method of solving the Green's function using modal expansion or the eigenfunction expansion method. So, our eigenvalue problem for the Green's function, the differential equation, this is the boundary value problem for the Green's function, is given like this, and what we discussed in the previous lecture was that the solution of this differential equation can be represented as an expansion in terms of the eigenfunctions of the unforced problem. So, the eigenfunctions of the unforced problem that we have already solved. So, if you substitute this expansion in the differential equation of the boundary value problem, then and remember that this Green's function these eigenfunctions already satisfy the boundary conditions. So, therefore, the Green's function is also guaranteed to satisfy the boundary conditions of the problem. Now, this is a linear differential operator. So, therefore, we can exchange this summation with the operator and rewrite this. And from the eigenvalue problem of this operator, we also know that so this is what we have. So, this is a statement of the eigenvalue problem, the differential equation of the eigenvalue problem. So, if you substitute in here and simplify, now to solve this equation for this unknown alpha k, we use the orthogonality property of eigenfunctions, which means I take inner product with w j on both sides, and using the orthogonality, then it filters out the jth term of this expansion. So, what we obtain is, upon simplification, so we have obtained the coefficient alpha j, and this can be done for all j 1 to infinity, and then we can solve for all these infinitely many coefficients alpha j. And once I have this, I can substitute back in here, and I have the series expansion of the Green's function in terms of the eigen functions of the problem. So, this is how we can also solve the Green's function in terms of the using the eigenfunction expansion, a method which we have also discussed in detail in the previous lecture. So, what we have looked at in this lecture today, we have solved the boundary value problem which arises in the force vibration analysis. So, this boundary value problem actually gives us a solution of the amplitude function of the particular solution. In this lecture today, we have solved that boundary value problem using the Green's function method, and we have looked at one example that we also and we took this the same example in the previous lecture, and we have got the same we have compared the solution with that obtained in the previous lecture. So, with that we conclude this lecture.